Okay, good morning, students. I hope you are all okay. As you heard, the lockdown has extended. The college may or may not open at the month of May. It may open at the month of May or it may open in the month of June, as said by the Honorable Chief Minister, Ms. Mamata Banerjee. So, in the meantime, we need to cover up our syllabus and be ready for the examination. Now, the last class we have discussed and we have completed the design and the analysis of eccentric connection. We have designed and analyzed the bolted eccentric connection. We have designed and analyzed the welded eccentric connection, and then we have discussed the various type of eccentric connections that are available, such as bracket connections, such as seat connections, stiffened, unstiffened. Then we have discussed framed connection, and then we discussed the steps, how to design that. We have seen some of the maths to design the connection, and finally we have done some examples and we have done some assignments. I have given some assignments. You have some of you have submitted it. So I think the eccentric connection is quite a bit clear to you now. The today's lecture is, we are going for the final stages of steel structure. Today's lecture will be based on basically plate girder. Today's lecture will be basically based on plate girder. What is plate girder? What is the importance of plate girder? What are the elements of a plate girder? What are the various design steps that are involved in a design of a plate girder? And finally, what are the how to design, and we will see one example in the next class. Basically, in today's class that will not be covered. In the next class, we will see that. Okay, so basically we will discuss all that today. So coming to the plate girder, what is a plate girder? Okay, let me open a example of plate girder. What is a plate girder? You have seen many times this kind of structure. I think you have seen many times this kind of structure. Okay, so basically in the bridge deck, basically the plate girders are used. Basically in the bridge decks, the plate girders are used. The bridge decks considered huge amount of load, basically rolling load as well as static load, dynamic load, earthquake load. Every load is acting on the bridge, which takes a huge amount of load. Now there may be so these loads are supported with the bridge decks. Okay, this length I cannot okay, yeah, from here to here, this length is called the bridge deck. The distance between two piers in a bridge is called a bridge deck. Now, when we are going for the bridge deck, the plate girders are very essentials, okay, because the decks are generally supported on plate girder. These are the plate girders, okay. These are the plate girders. You see, basically they are the most important part of the structure, okay. They consist huge, they are used because huge amount of load has to be delivered or has to be carried, okay. So basically these are the plate girders. Now coming to the design procedure. What are the design procedure that involves in a plate girder? Okay, we will see the various design procedure. We will see the various design procedure. We will see what are the IS code prescribed values, guidelines for the plate girders. We will see all that. Okay, now coming to the plate girder. Okay, now coming to our materials for today. Now, design of plate girder. Okay, now when the spans are very large span, because bridge decks, bridge decks and maybe some of the warehouse, etc., The span may be very, very large, and for that spans, very much huge amount of spans, normal rolled section, rolled beam that we have designed, the beam section, because when the bridge structure, there will be deflection. A bridge, if consider, we go for that picture again, if we go for that picture again, let me go for that picture again. Let me go for that picture again. So in this picture, you can see these bridge decks should be designed for their deflection, how much deflection they can carry. So as these structures are huge and huge amount of load they have to carry, okay, huge amount of load they have to carry, for that this normal I section, in the beam we have designed a normal rolled I section with cover plates, that is the built up I section we have designed. So built up I section are not sufficient to carry that load. Okay, to support that load, normal I sections are not that much sufficient. So we have to think of some other material, some other section, so that the load can be carried, because huge amount of load is carried. Now there are some alternatives to that. Number one is plate girder, number two is truss girder. Okay, number one is plate girder, number two is truss girder. So what is coming in the plate girders? Plate girders are very much moment resisting. Plate girders has their moment resisting capability. That means that they can resist the moment that coming from the huge amount of load in between the rolled I section and the truss girders. Okay, rolled I section and the truss girders. Now, what is a plate girder? A plate girder is basically an I section. But what is the difference between the rolled girder and the plate girder? Rolled I section and the plate girder section, that is, in the plate girder section, all the sections are built up. That means there is no rolled section available. Built up sections are used to create a plate girder. In the example, if we see, this is a plate girder, where this is a separate flange plate. This is a separate flange plate. This is a separate wave plate. Flange plate, wave plate are separate with each other. In the rolled I section, we can see that if it is a rolled I section, then if this is a rolled I, so if this is flange, if this is wave, they are connected to each other. That is a rolled section. Okay, rolled steel section. But here the rolled steel section, the flange and the waves are not connected. They are connected with the help of some connection. That means welded or bolted connection. They are connected to each other. So the plate members, flange plate and wave plate, or there may be flange angle and anything, so they are connected to each other with the means of connection. So it is a complete built up member. Okay, complete built up member. Now built up flexural member, they are built up flexural member. So what is the importance in built up flexural member? That is, the designers they have a great the designers have a great place. The designer has a great, they have great flexibility in the design of the wave portion, because all the plates that will be connected are built up. That means they can design each plates, each members, wave or flange by their own. So they have great freedom in the design of the plate girder. Now this is a example of what a plate girder looks like. Okay, this is the example what a plate girder looks like. It is you can see it's a bridge deck which is provided. Okay, generally in normal cases in the bridge, you can see you have seen as our college in Dum at the Dum station also, there are still bridges at the starting of the station. These bridges, if you can see closely, after the college opens, if you can see closely, you can see there is also plate girders are used. Okay, so there is a plate girder. Okay, now what are the so This now coming the what is the plate girder arrangement. There are the various plate girder arrangement. There may be bolted connection, there may be welded connection. First coming to the welded connection. So this is the web plate, this is the flange plate. This is the web plate, this is the flange plate. Now this connection is provided here. So the web and the flange are together connected with the weld connection. Okay, but in case of the bolted connection, generally in all the cases welded plate connection is always preferred, and it is always done. Bolted plate connection is not preferred, and we will not see any examples of bolted plate connection in our exam. In our lecture, we will see all the exam based on the welded plate girder. Okay, bolted plate girder is also there. Bolted plate girder, and now this is the web plate. This is the web plate now, and this is the flange plate. Now in the welded connection, this web and flange can be connected with weld, but there cannot be any bolt at the connection. So we have to provide another extra member to connect the web with the flange. So for that, flange angles are provided here. These are the flange angles. So flange angles are provided to connect the flange plate with the web plate. Okay, the bolted connection are very much the bolted plate girder connection are not used nowadays because the welded connection are there, and there are no in the welded plate girder connection there is no requirement of the flange angle. So the flange angles are sometimes the bolted plate girder are not generally used. Okay, so these are some of the typical arrangement of plate girder that are used. Now design of a plate girder is essentially an exercise ordinary beam design. That means in the beam design, if you can remember in the beam design what we have discussed, that is we have determined the moment carrying, that is the moment capacity of the flange plate. That means how much moment the flange plate can carry. So first one, proportioning of a member with a section modulus adequate to resist bending. That means the section should have a section modulus so that it can resist the bending. The bending is basically raised by the flange plates. Okay, so the flange plates are used to resist the bending. So the design of the flange in the plate girder connection, the theory is same. In the plate girder connection, the flange plates are designed so that for the moment capacity, it is checked for the moment capacity. If it is sufficient to check the moment, this is the first thing. And the second one we check in the normal beam design is the buckling capacity. That means the shear carrying capacity of the web, because the web is a very thin member, so it acts as a compression member, that is a column. So column is a compression member, so there will be buckling of the column. So web capable of resisting shear. So due to the web becomes very thinner, there will be buckling of the web. Buckling of the web is one of the most important phenomenon in the beam design. We have seen web buckling and web crippling phenomenon because the web acts as a column member. So the buckling phenomenon has also to be checked. Okay, so this is the buckling phenomenon that we have given here. So basically the two parts of the design we will be proceeding. Number one is the design of the design of the flange plate with moment capacity, and the second one is the design of the web plate to resist the shear, that is the buckling proportion. So we will need to design all these two based on that proportion. Now, as I have told you in the earlier section, that is in the plate girder design, the designer has the flexibility to design the web portion. Okay, because the buckling of the web will be there. Okay, the buckling of the web will be there. Now, so as we are, if you in the picture, if you see, this is the flange plate and this is the web plate. So if the flange plate and the web plate, both has the web plate is very much thinner in their thickness. So as the web plate is very much thinner in the thickness, there will be and there has to be some buckling. So the web should be sufficient to buckle. Now as the designer has that flexibility in the design of the wave section. They can make the wave thicker. They can make the wave thicker. Okay, they can make the wave thicker, but generally this criteria is not adopted because they can make the wave thicker, and also they can provide the most important thing of plate girder is stiffener. Okay, what is a stiffener? In this picture you can see they are the stiffener. This is a stiffener, this is a stiffener, this is a stiffener. So there are stiffeners they are provided. Okay, so these are the stiffeners are provided to stiffen between the bolted the wave and the plate member. So they are used to stiffen the bolted and the wave member. So stiffener are used so that to increase the shear capacity of the wave. Okay, there are various types of stiffener. First is the longitudinal stiffener and the transverse stiffener. So in this picture that I have shown you, you can see longitudinal as well as transverse stiffener are shown. If this is the normal plate girder design, longitudinal transverse stiffeners are of two types. Number one is the stiffeners that are provided at the end. So this is the stiffener that is provided at the end. Consider that thing. So in the end, this stiffener is provided. Consider at the end, this stiffener is provided. It is called the bearing stiffener or the end bearing stiffener. Okay, bearing stiffener or the end bearing stiffener in a bearing why this stiffener is provided at the end? Because the shear action will be more at the end. If you see, let me show you. If we proceed a bending moment diagram, let us show you a bending moment diagram. Okay, then it will be understandable to you. Consider this is a load acting here. It is a simply supported beam. It is a simply supported beam. The load is acting here. Now, what will be the or it may be a UDL. Generally, a UDL is there. Generally, a UDL is there. Okay, no, not a simply supported. Sorry, not a point load. A UDL, that is the uniformly distributed load, is acting here. Now, if the load has W, kilonewton per meter, W kilonewton per meter load is acting, then what is the bending moment and shear force diagram? The shear force diagram is like that. I think you know this is the shear force diagram and this is the bending moment diagram. So you can see the maximum amount of shear force is acting at the support. So maximum amount of shear force is acting at the support. So to take this extra shear force, the end bearing stiffeners, the bearing stiffeners which are provided at the end is called end bearing. Generally, end bearing stiffeners are used. So the end bearing stiffeners are used at the end. This is the number one transverse stiffener, and the second transverse stiffeners are this called intermediate transverse stiffener. These are called intermediate transverse stiffener. Okay, I think it is clear to you what is intermediate transverse stiffener and what is this, that is the normal bearing stiffener. So intermediate transverse stiffeners and as well as the bearing stiffeners, these are all used in case of the in the section of transverse, that is the vertical stiffener. Okay, vertical stiffener. Now, so this is the vertical stiffener. Now coming to the horizontal or longitudinal stiffener. Okay, the longitudinal stiffeners are also produced if it is needed. The longitudinal stiffeners are also used to resist the extra force in the girder. So these are the stiffeners. This is the use of stiffener to increase the wave area. So if we use this area, so you can see this is the actual wave. Now the wave is becoming that structure. Now the wave is becoming that, similar here it is also that. So this is the wave. To enlarge the wave area, to make the wave area more, to increase the wave area, we use the stiffeners. Okay, so this is the use of stiffeners. So in a normal elements of plate girder is a wave plate, flange angles with or without cover plate for bolted, that I have shown you like here. Okay, and bolted and welded bolted connection or bolted plate girders, and only flange plate for welded plate girder, that is the normal plate girder that we provide. Okay, then stiffeners, bearing transverse and longitudinal, bearing stiffeners, transverse stiffeners that I have told you, intermediate transverse stiffeners and longitudinal stiffeners, and splices for wave and flange. So these are the various elements that is present in a normal plate girder. You can see in the picture also there are these elements I have shown here. Now, the name of the issues are here. So this is the flange plate, this is the web plate, this is the bearing stiffener, and this is the transverse stiffener. Okay. Now coming to the complete design of plate girders. What are the various steps or the various elements that need to be designed? What are the criteria that need to be designed in the plate girder? Calculation of the external loads, okay, external loads and the estimation of the self weight, because the plate girder will be loaded by the external load as well as the self weight of the plate girder. So when we are calculating the external load and the self weight of the plate girder, so external loads and the plate plus the self weight of the plate girder we have to consider, so that the total load is coming to us. Now then we have to calculate the shear force and the bending moment that we know, because the shear force is needed to calculate the shear capacity and bending moment of the bending or the moment capacity. Then the depth. So if we got the shear force and the bending moment, you can determine the deciding depth of the plate girder. Then the web of the plate, the depth of the plate girder, depth of the plate girder, depth of the web plate, depth of the flange, curtailment of the flange plate. Curtailment of the flange plate is a partial. You can do that, you can not do, you cannot, you may not do that. Okay, curtailment is not generally required. We will not see that in our example. Design of connection, that is the most important, flange plates and angles. Okay, or in case of web, in case of welded connection, flange plates and the web plates. Design of connection between the flange plates and the web. Design of stiffener, that we will see intermediate and vertical, intermediate transverse and bearing stiffeners. Design of web splice, design of flange splice, design of end connection, that is the welded or bolted. So this all we will see through our study. What are the design steps? Now we will discuss. So coming to the design steps, so we will see that all these criteria, some of the criteria will not be there because this is beyond your syllabus, but you will see various criteria. More than 70 to 80% criteria we will complete in the design steps. That are the very most important for us, the design steps. Okay, the design step is very much longer process, and design steps consist very much thorough analysis. Now to analyze the plate girder, you need the concept of both beam design, both column design, both welded and welded connection, generally welded as well as bolted connection. So complete design procedures. Also the tension member we will need. So complete design procedures of all, the knowledge of complete design procedures of all these previously discussed chapters in your steel structure, we will need all that. Okay, now coming to the design steps. Now what are the data that are available to us when we are that will be available to us when we are opting for the design? Number one, what is the load acting on the member and what is the length of the member? That means the length of the girder will be given to us and the load acting on the girder will be given to us. Okay, so these two data will be given to us along with may or may not be the steel grade that will be used, that will be given to us. Now, so if these two data are given to us, we will follow this procedure. Step 1, first assume self weight of the girder and determine total load. Now the self weight of the girder, as the load is acting, the self weight, so self weight means the total weight of the plate girder, that means the web plate and flange plate with stiffener we have to calculate. Now we do not know what is the flange plate weight, what is the web plate weight, what is the weight of the stiffener, we do not know. So if we want to consider, we do not know that. So we do not know what are the various weights of the various members in a plate girder, so we have to assume the self weight. Basically an empirical formula is used. Okay, the empirical formula is, which is assumed as W by 200 to W by 400. So the value of the plate girder is assumed in between that, W by 200 to W by 400. In between that we will assume the self weight of the plate girder. So now what is W? W is equal to 1.5 into W dash into L in kilonewton per meter. That means 1.5 is the load factor, that is the factor for the limit state design. W dash is the applied load on girder. There will be applied load on the girder in kilonewton meter. Now very much important thing, that it is the unit having kilonewton per meter. That value should be given to us. Okay, If it is not kilonewton per meter, then we have to change it to that. Okay, so 1.5 into W dash into L. This is the formula for calculating the capital W, that is the cell weight. Now, so this is the 1.5 into W dash into L is millimeter kilonewton per millimeter. So W we know, dependent on the W dash, we will calculate then. So if we can determine the total cell weight of the member, that is from W by 200 to W by 400 value. So in the total factored load that will be acting on the plate girder, the P will be equals to W cell weight that we have calculated that value here, plus 1.5 into W dash. That means the W dash, that is the extra load is acting. So this is the imposed load. Okay, imposed load, or the combination of maybe the combination of dead or live. Okay, maybe the combination of dead or live. So total that load, the cell weight plus the actual load acting on the member, we have to consider. So the load may be like that. It may be a uniformly distributed load, it may be a point load, or it may be mix of that. So this total factored load has to be calculated. This is the first step, the load calculation. So first we have to determine what is the load coming on the girder. Second step is the determination of bending moment and shear force. So then the bending moment and the shear force we need to find. So what is the bending moment and shear force coming to the plate girder? So if generally a UDL is acting, okay, let me erase that. If generally a UDL is acting, I have shown here also, you can see that here also, if a UDL is acting, so this is the bending moment diagram and this is the shear force diagram that I have told you also. The maximum bending moment for a UDL for a simply supported beam is WL square by 8, and the shear force for a normal simply supported beam with UDL is at the end it will happen like WL by 2. I think you are at the third year of BTech, so you should know how to calculate the bending moment and shear force. So it is only for the UDL. So PL square by 8 and PL by 2. That is, so maximum bending moment is denoted by MZ and maximum shear force is denoted by VZ. Now sometimes there may be point load also. There may be combination of 2-point load or 3-point load with bending with moment. So for that we have to determine the shear force and the bending moment diagram first. So the knowledge of the basic knowledge of the shear force and bending moment is also required for us, because at the first we need to determine also what is the shear force and the bending moment maximum. So if the load is not UDL, if it is a combination of UDL and point load, then for that we need to determine the bending moment and the shear force diagram. Okay, and the maximum bending moment will be calculated. That I have told you here also. Okay, so this is the second step, determination of the shear force and the bending moment. Now coming to the step number 3, that is another step, that is the design of the plate girder. Design of the plate girder, that means we have to determine the area of the wave and the area of the flange. We do not know that, so you have to determine that. The first is the depth of the wave D. Depth of the wave D. So this is the flange, this is the wave. So we will first determine the depth of the wave, optimum depth of the wave, that is the depth of the wave that will be needed to us, determined by that formula. Okay, determined by that formula. D is equal to mz into k divided by fy to the power 0.33. Mz value we have calculated here. The value of the mz we have calculated PL square by 8 for normal UDL load. We have calculated fy we know, and k. What is k? Wave slenderness ratio. That means the slenderness ratio of the wave only. What is the meaning of slenderness ratio? That is the value of the L by a normal K into L by R, that is the least radius of gyration. In case of wave, that is the slenderness ratio is the D by TW, that is the wave slenderness ratio. Now we do not know the value of wave generally. In general, K is assumed in the range of 135 to 240. In between this range, K is assumed in 135 to 240, in between that range. Now, you need to understand here something. If K is on the higher side, consider K is taken on the higher side, what will happen? What will happen is this value of k is on higher side, that means higher. So the value of the d will be higher. So the plate will become longer. So the effect of the shear buckling will be high in case of that. So always try to take the value of the k in a lower side. Okay, always try to take the value of a k is in the lower side, so as to get a nominal or a standard value of the depth. So as to get standard value of the depth, then we can determine, if we get a standard value of the depth, then so if we take a standard value of the depth, so the less will be the requirement for the transverse stiffeners, because the transverse stiffeners are used to resist the shear buckling. Okay, so less will be the requirement of the transverse stiffeners. So the value of the k should be taken in the range. Now the d by tw should also satisfy the following criteria. The criteria I have given. Now if now in the math there will be mentioned that wave without transverse stiffeners, or wave with transverse stiffeners, or wave with horizontal stiffeners, there will be mentioned in the math. Now if the k by dtw shall satisfy the following condition. Clause 8.6.1.1. So let us come to clause 8.6.1. Okay, now I have opened here the values. Okay, you can see from here, that is the value. Now what is the criteria? The criteria is, let us come down to the criteria. Okay, in the above side. Okay. Okay, we have come to that. Now, so this criteria should be minimum wave thickness. When we are determining the wave area, this area calculation should be there. So first check is for the serviceability requirement. If for wave without stiffener, for wave without transverse stiffeners, if in the math it is specified that the wave is without the transverse stiffeners, for that we have to use that criteria. For serviceability requirement, d by tw less than equals to 200 into epsilon. What is epsilon? We know epsilon is equal to root over of 250 by fy. That is the value we know, root over of 250 by fy. So d by tw less than 200 epsilon is the value of the serviceability requirement when transverse stiffeners are not used and wave connected to flange along both longitudinal edge. That means this is the wave connected with the both longitudinal edge. Okay, so this is the first criteria, serviceability criteria, and the second one is the compression flange buckling requirement. Clause 8.6.1.2. Let us come to clause 8.6.1.2. Okay. All right, let us come to clause 8.6.1.2. I think we have to download it, I think. So in the serviceability criteria, that is clause number 8.6.1.2, we can see that is the compression flange buckling requirement here. The d by t transverse stiffeners are not provided. It should be less than, if we zoom it, okay, you can see that d by tw less than equals to 345 epsilon f square. So epsilon f means the same value s square. So less than that value. So this criteria, if the transverse stiffeners are not used, okay, this criteria if transverse stiffeners are not used. Now second is for wave with transverse stiffeners. There may be transverse stiffeners also. So if the wave is with transverse stiffeners, this criteria has to be satisfied. Clause number, this clause. Okay, now for this is a serviceability requirement. Now this is the so when transverse stiffeners are provided. So first 3D. So this, now what is C? C is the spacing of the transverse stiffener. In the picture you can see here also, in the picture you can see here also, I have shown it here that if this is the transverse stiffener, bearing stiffener and end post, that is the end post, that is the bearing stiffener, we do not need that. So this is the transverse stiffener. So if this is the transverse stiffener, this is the spacing between that. So transverse, if this is the wave flange portion and this is the wave, so in between the wave transverse stiffeners will be there. So the spacing between the transverse stiffeners is called the spacing. So we have to first determine the spacing. So we will see how to determine the spacing in the next parts also. But if in the math the transverse stiffeners are given, if in the math the transverse stiffeners are given, then we have to determine that also. Okay, so you will determine that in the next steps. Okay, so if we can determine the value of C, so you have to check that. So for 2.4 D less than equals to C less than equals to D, this criteria, for that this criteria, so its value are given here also. Okay, for here the value are given here also. Okay, so also okay, these are the values, I think, wave stiffeners. Okay, these are the values which are given. So 1 to number 4, these are the values to be given for transverse stiffeners and longitudinal transverse stiffeners. Okay, now this is the values 1 to 4. This is the values for the serviceability requirement, and the value for the compression flange buckling criteria when transverse stiffeners are provided. Then when, so here two criteria, depending on the spacing, C greater than equals to 1.5 D and C less than 1.5 D, they are the two values. So depending on the value of the C, so you can see when the transverse stiffeners are being used, then the criteria is basically depended on the ratio of the D by TW, that is the ratio, the ratio of the C, the value of the C, it depends on. So you have to determine the spacing here also. You will see how to determine the spacing in the next step. So we will need that. Now compression flange requirement, so this is for the only transverse stiffeners. Now sometimes along with transverse stiffeners, some horizontal stiffeners will also, longitudinal stiffeners will also be used. So if horizontal stiffeners are used, so coming to criteria number 2, when transverse stiffeners are and longitudinal stiffeners at one level only are provided. That means transverse stiffeners and longitudinal. So only one level the longitudinal stiffeners are providing. What is the distance? 0.2 D from the compression flange. So this distance is 0.2 D. So this distance is 0.2 D. So for that, this is the criteria to be satisfied. Okay. So here it is also mentioned here. So here it is also mentioned that this is the criteria to be satisfied here. And the last one, D, when second longitudinal transverse stiffener at the distance of the neutral axis, that means this is the neutral axis. So here there will be another horizontal bar longitudinal stiffener is provided. So 4 criteria is there as per the IS 800 that we have seen. So depending on the stiffener used and not used, whether there will be stiffener used, whether there will be not any stiffener used, whether there will be transverse stiffeners or longitudinal stiffeners or both, depending on that there are the criteria that are specified. So this is the 4th criteria we have to satisfy. Okay, now 4th criteria we have to satisfy that. Now, so this is the criteria. Now when coming to the 3rd and 4th criteria, there will be no requirement of the compression flange buckling because horizontal stiffeners are provided, so there will be no compression flange buckling criteria required. Okay, so this is the value of the, so that's how the value of the D by TW, that is the value is calculated, and the optimum depth of the wave is determined. So depth of the wave we have got. Now we have to determine the thickness of the wave. The thickness of the wave is determined by that formula. Optimum wave thickness is determined by that formula, my mz by fy by k square to the power 0.33. Now we know the value of k mz, so the optimum wave thickness will be determined. So wave design is complete. So we have designed one part of the plate girder. We have determined one part of the plate girder is the wave member. Now coming to the flange member. Now the flange plate will be designed. The area of the flange plate, are determined by that formula. AF equals to mz into gamma m0 divided by fy into d. Mz value we know, that is the bending moment, maximum bending moment. Gamma m0 we know that is 1.10 we know, and d. The d we have determined. Depending on the d, it will be area of the flange. Now if we know, so this is the flange plate. Beyond that, this is the wave. So flange plate area we have know. We know. Now to determine the dimension of the flange plate, that is the BF and the TF, that is the width of the flange and thickness of the flange. Now how to determine that? Now for non-composite plates, what is the meaning of composite plate? If this is a plate girder, and composite means this is one material material 1 and this is material 2. So a composite material is there. So more than one material is used for the creation of the section. So for composite, non-composite planes, that means a non-composite planes. Okay, so non-composite plates. So if it is a non-composite, that means the plate. So two materials are same. That is the normal case we will discuss. So for that, the width of flange to the depth of the wave ratio is taken 0.3. That means width of the flange means BF by depth of the wave, that is equals to 0.3 for non-composite plate. And for composite plate, it is taken as 0.2. So for composite plate it is taken as 0.2. In our math, all the section will be composite section, non-composite section, so we will use the value of 0.3. Now if we can got the value of 0.3, so from here we can determine the value of BF, that is the width of the flange, and from here we can determine, so width of the flange is determined, so the thickness of the flange, that is the TF, will be AF by BF, that is the area of the flange divided by the width of the flange. So we can determine the thickness of the flange. So up to that step we have determined all the required values. So depth of the wave, thickness of the wave, depth of the flange and the thickness of the flange, we have determined all the values. Now coming to the section classification, step number 4. So we have determined the section. Now the section classification is very much important. Now why the section classification is important? Now if you can remember, in the beam design, the moment capacity, that is the beta B, is dependent on the section. What is the section of the flange? Because the flange member, always the flange is the susceptible member in the bending. So the flange will be acting on the bending. So the section classification has been done. For a plate girder, the flange of the plate girder is always should be kept in plastic section. So there are 4 section, you know: plastic, semi-plastic, compact and compact. And slender is not used in India, that I have told you, if you can remember. So always try to take the section in a plastic section, the flange. So for that, now coming to the chart. Now let us come to that chart value. Okay, so here, so this is the chart value. So now, as it is the outstand element, where it is, okay. Okay, so outstand element of a compression flange. So this is the, let us come to the next picture. So for our case, this will be the member, because it is the built up member. So outstand element of a compression flange, if this is a rolled section, then it is 9.4 epsilon, given here also, and for a welded section it is should be less than 8.4 epsilon. So we have to take the value of the B, that is the, what is the meaning of B? B is the distance between the edge of the wave to the end point of the flange. This is called the B. So we have to take the value of the BF, that is the sorry. So we have to take the value of the BF, that is the width of the flange, in such a way that the BF B by TF ratio comes in between 8.4 epsilon for welded and 9.4 epsilon for rolled section. So you have to take that value according to that. Okay. Sorry. Now this is for step number 4. Coming to step number 5. What is step number 5? The moment capacity, clause 8.2.1.2. Let us come to clause 8.2.1.2. Okay, so this is the clause 8.2. Okay, this is the clause 8.2.1.2. This is the moment capacity. What is the moment capacity? So you know this formula we have used in the bending moment design also, in the beam design also. So the moment capacity is the formula beta B ZP Fy by gamma m0. What is the beta B? Beta B that I have told you. So beta B Zp by gamma m0. So beta B is equal to 1.0 for plastic and compact, and beta B is equal to Zd by Zp for semi-compact, that we know. I have written here also. Zp is the plastic section modulus of the flange member only. So we have to determine the plastic section modulus of the flange only. This is the flange. The plastic section modulus has to be determined by the flange only. What is the plastic section modulus formula that I have told you? It is the formula A by 2 y1 plus y2. A by 2 means the total area by 2. So if we use that formula we are coming. So A is equal to A by 2, that means BF into TF, 2 into BF into TF, because this is the two numbers of flange, by 2 into y1 plus y2 means the distance between. So if this is the equal area axis, that distance is y1 and y2. y1 plus y2, that means the distance between total capital D minus the thickness of flange by 2. That is the this is the distance between the y1 and y2. So this is the formula we will use to determine the plastic section modulus of the flange member. Okay. So by using that formula we have got, and D is equal to the overall depth of the girder. That means the total depth of the girder. This is the total depth. That means small d plus 2 into thickness of the flange. So putting that value, the MD should greater than the MZ. That is the check for the buckling bending criteria. That is the moment capacity. So the moment capacity should be always greater than the bending moment that is acting on the beam and girder. Second is the step 6 is the shear capacity of the wave. That is the most important, because the most important member of the plate girder is the wave of the plate girder. So the shear capacity of the wave is also very important for us. So what is the shear capacity of the wave is calculated? How it is calculated? They are calculated by two methods. Simple post-critical method. So coming to the formulas, where is the formula? Okay, let me come to that. Okay, so shear buckling criteria, shear capacity. The method are: number 1, simple post-critical method. Simple post-critical method can be used for cases. Here it is said that the simple post-critical method based on the title shear buckling can be used for waves of I section girders with or without intermediate transverse stiffener. That means if the girder is with the transverse stiffeners or without the transverse stiffeners, this method can be used for both the cases to determine the shear capacity. What is the shear capacity? How to determine? That is Vn equals to Vcr. That is the Vn, that is the shear capacity. Nominal shear strength of the buckling is given by Vn equals to Vcr. What is the Vcr? Here it is all mentioned here. What is Vcr? Av into tau b. Tau b is depending on the lambda w. That is the lambda w means the non-dimensional wave slenderness ratio. So wave slenderness ratio, all the values are given here. As per the code, I have written all the values. So lambda w is equal to f square tau cr is equal to that value. Now coming to kv, kv is equal to, depending on the value of Poisson's ratio, kv is equal to 5.35 when transverse stiffeners are provided only at the support. That means the bearings transverse stiffeners are only provided at the support. That means the bearing stiffeners are provided, no intermediate stiffeners. So there will be no requirement of any spacing. But when the intermediate transverse stiffeners are provided, then we have to calculate the spacing for the intermediate transverse stiffeners. So for that, there are the two values, wave without transverse stiffeners and 4.0 plus J when CRD at the spacing of the transverse stiffeners. Here at this stage, we have to determine the spacing of the transverse stiffener. How to determine that? We will now see. So how to determine the spacing of the transverse stiffener? So what is the spacing? This is the spacing of the transverse stiffener. The distance between two intermediate transverse stiffeners is the spacing. So calculation of the spacing of the transverse stiffeners. First, assume C by D, that is the empirical formula here also. C by D, that is the spacing by the wave depth, depth of wave between 1.2 to 1.6 we have to assume. Then the C is calculated from then. So we know the value of D, then the C, that is the spacing, is calculated based on that. So based on that, the spacing is calculated, and that it is based on that formula. Okay, so the C is checked for the following. So the value of the C is calculated. Putting all the values here, we can get Vn equals to Vcr. So this is the value of the Vn. So this is the first formula. This is the simple post critical method. Coming to the second formula, that is the tension field. Second formula is the tension field method. That is, the tension field method is adopted. Here it is said that may be used for waves with intermediate stiffeners. That means this method can only be used if the wave is with intermediate transverse stiffeners. Okay, in our math we will always try, I have mentioned it in the later stage also, we will always try to do the math, do the to calculate the shear capacity by simple post critical method. Okay, always try to do that. Okay, but if it is specified in the math that we have to use tension field method, then we have to use tension field method. So what is tension field method? When the plate girder is with transverse stiffener, the method we applied, I have told you from the code. So this is the formula. Here it is said that Vn is equal to Vtf. Vtf equals to that value. It is given here, it should be less than the Vp, that is the applied load Vp. What is the Vp? I have also told you here. So Vn equals to that formula, Tb is equal to as calculated in the previous method. So Tb we have determined here. Tb, we have determined the value of Tb here. So Tb will be required for here. If V is from that formula, Xi here is given, phi is given, WTF is also given, C spacing is given, all the values are given here. Now when F MFR is here. So MFR equals to that formula where NF equals to MZ by HF. We know that Vp is equal to, now what is Vp? Vp is equal to the applied shear Fy by D into TW. Vp is given here. What is Vp? Vp is here, it is given. Vp is equal to, as per the clause number 8.4.1, this is the value of the Vp. That is AV into FyW by root 3. I have told what is AV. AV is equal to the, for welded section, D by TW. Also because we are determining the shear capacity of the wave, so D by TW value will be required. So D by TW, from here the Vp is calculated. Okay, I have mentioned here also, always try to use the simple post critical method. So depending on the all the formulas now, what is HF? The distance between the CG of the wave, the CG of the flange. So if the CG of the flange value is known to us, then we can determine the HF value. So depending, always try to use the simple post critical method. And finally, if, that is the main thing, if Vn by gamma m0, that is the Vn by gamma m0 means Vd. So if Vn by gamma m0 greater than the maximum shear force Vz, the value, then there will not any requirement, any transverse stiffener. Okay, intermediate transverse stiffeners will not be necessary because the shear capacity is more than the shear force. But if the shear capacity is less than the shear force, design shear capacity is less than the shear force, then the intermediate transverse stiffeners will be required. Then we have to design for the intermediate transverse stiffeners. End bearing stiffeners will be required because to resist the extra shear force that I have told you, because from the shear force diagram. But transverse stiffeners is required only when the moment capacity, shear capacity is less than the applied shear force. So for that we have to design the transverse stiffener. So the basic design of the plate girder is over. Now we will go into the design of the stiffener. That is the important portion for us. What is the stiffener? Now coming to the step 7, the design of the end bearing stiffener. So there are two types of stiffener I have told you. When it's coming, let us come to the above picture that I have told you that what is the end bearing stiffener. I think you can remember, this is the end bearing stiffener that is provided at the end because to resist the extra shear force, and these are all the transverse stiffeners. So first we have to design the end bearing stiffener. So let us come to end bearing stiffener. Now first the local capacity of the wave is checked. Local capacity of the wave is checked by the following formula. This is the formula to check the local capacity of the wave. Clause 8.7.4. Let us come to clause 8.7.4. Okay. 8.7.4 clause is here. So bearing stiffener. Okay. It is said here the local capacity of the wave Fw is given by that formula. B1 plus N2 into TW by FYW by gamma M0. It should be greater than the Vz. Now, then no requirement of the bearing stiffener. Now, if the Fw, that is the local capacity of the wave. So, if the local capacity of the wave is higher than the shear capacity, it is not generally happen because the local capacity is very much less than the shear force applied. It always that if it is more than that, then the bearing stiffeners will also not be required. But generally, the bearing stiffeners are required. So Fw always less than Vz, then the bearing stiffeners will be required. So where B1 is the stiff bearing length, Now, this formula is for the wave buckling criteria that I have told you in the beam design. So, what is the value of B1 if otherwise specified? The value of B1 is taken as 100 mm. I have told you in the wave buckling criteria also the value of the B1 is generally taken as 100 mm. Now, what is the value of N2? 2.5 into TF. So, where from it is coming? If you can remember, I have told you if this is the wave, this is the flange. So, for that in the picture it is also said here, if this is the wave, the flange, there will be 45-degree dispersion value here. So, 45-degree dispersion value here. So, for that value has to be taken. So, from here the value of the 2.5 into thickness of the flange is coming to that criteria. Now, bearing area. So, B1 is coming, B2 is coming. So, TW into FYW by gamma M0. So, this is the total. So, the local capacity should be checked first. Now, if the bearing stiffeners are required, we have to design for the bearing stiffener. How to design that? So, the bearing area of the wave bearing stiffener is the area, how much area is required for the bearing stiffener is calculated from the clause number 8.7.5.2. Let us come to clause 8.7.5.2. So, this is the 8.7.5.2. Let us coming to the code. Okay. So, this is the formula for carrying the bearing stiffener. So, AQ we need the bearing area. So, bearing area is equal to 0.5 into FPSD by gamma M0 by Fy. So, FPSD is the design shear force that we have calculated. Now, then an appropriate section for the stiffener is selected. Now, we have calculated the AQ. Appropriate section is assumed, is selected. A trial section, generally a ISF plate is selected. Okay, I have told you there ISF plate is provided. So, the area provided here will be 2 into the area provided for stiffener, because if this is the wave of the girder, here is one stiffener, here is another stiffener. Always 2 bearing stiffeners are provided. Let us come to the picture that I have shown you. Let us come to the picture that I have shown you here. Always 2 bearing stiffeners are provided. Always 2 bearing stiffeners to balance the shear force, shear action. So, 2 into the area provided. Okay, 2 into the area provided. 2 into the area provided for the stiffener. So, the total area provided, it should be greater than the AQ, that is the area required. Now, coming to the check for the outstand of the stiffener. Now, this is the wave, and this is the end bearing stiffener. So, outstand BS value should also be taken. So, how much outstand value of the stiffener we can provide? Clause 8.7.1.2. Let us come to clause 8.7.1.2. Okay, this is the outstand of the wave stiffener. Okay, it may be transverse, it may be wave, it may be bearing. So, outstand of the wave stiffeners. Outstand of the wave stiffeners is between 14 TQ and 20 TQ into epsilon. So, it should be always less than 14 TQ and it should be always less than 20 TQ value. So, it is written here also. So, what is the value of TQ? Thickness of the stiffener. So, we have determined the thickness of the stiffener here. So, depending on that, the value of the outstand, this is the outstand of the stiffener is determined. Okay, very much important part, we have to check for that also. Now, the check for the buckling of the stiffener. Now, we have determined the stiffener. So, if let us come to the picture again. So, if this stiffener is designed, so it has the same depth as the wave, depth of the wave. So, it should always be checked. It is also checked for the column buckling criteria. So, it is also designed as a column. So, how to do that? Here it is said that now the stiffener plate is checked for the buckling resistance, which is dependent on the calculation of the design compressive force for the effective area of the stiffener. Now, when the complete arrangement of stiffener, end bearing stiffener and the wave is used, some portion altogether act as a column. This is the total altogether area. This is the total altogether area that act as a column. This is the total altogether area that act as a column. Okay. So, when we are determining the buckling resistance, we have to determine the buckling resistance of that area. So, that effective area first we have to calculate. So, the effective area of that section will be 2 into Bs into Ts, that is the area of that part and that part, and for that part from here to here it is 20 into Tw. It is mentioned here also. Okay, let me check that. So this is the total distance from the horizon, the wave part, that is the from the center of the center of the flange, center of the stiffener to the edge of the wave area. It is 20 T into W. So 2 into T into W into the TW is the total effective area. Now then the IXX, that is the XX section, that is the that section for the birth stiffeners are determined with respect to the central line of the wave. Now why it is determined as the central line of the wave, I will tell you in the later part. Okay, why it is determined with respect to the central line of the wave. So when it is determined with respect to central line, we have to use the theorem of what is that, parallaxis theorem, to determine the area moment of inertia for that. So R is equal to the R, that is the least radius of gyration I by A, you know. Then the slenderness ratio is determined by lambda is equal to KL by R when K is equal to 0.7, because all the parts are restrained together, so 0.7 will be used. So and L is equal to the depth of the wave. Now L for the member, that is the L is the depth of the wave. So this is the length of the stiffener. Length of the stiffener is that which is equals to the depth of the wave. Okay, the depth of the wave equals to depth of the wave. So here it is said that, so the KL by R ratio, the FCD is determined, FD is greater than VZ. Buckling class C, because why it is buckling class C? So you know that for any composite member, here it is mentioned here also, if you can see here, if you can see here in the compression, the design, there I think it is, where it is, here it is said that for any channel angle T and solid section, okay, it is a solid section. So for that always any C class will be used. So buckling class C will be used here. So that this is the design of the bearing stiffener. Now coming to the intermediate transverse stiffeners, it may be required depending on the shear criteria that we have discussed. So if in the math it is said that intermediate transverse stiffeners are required, or in the value of the shear capacity we have got the value of the shear capacity less than the shear force, then only we have to apply the intermediate transverse stiffener. The intermediate transverse stiffener design, step number 8, is similar to that case of the bearing stiffener. We have to calculate for the capacity. It is some different, but then you have to check for the outstand, then you have to check for the, then we have to also check for the buckling. It is quite a bit same, but again we will see that. Now first the intermediate transverse stiffeners. Now the intermediate transverse stiffeners has a very important property, that it is spacing. So the spacing of the transverse stiffener is depth of the firstly the spacing of the transverse stiffener divided by the depth of the wave is found. Clause 8.7.2.4. Let us come to clause 8.7.2.4. Okay, 8.7.2.4. Let us come to that. Okay, 8.7.2.4. This is the 8.7.222.4. Okay, so minimum stiffeners, transverse wave stiffeners not subjected to external loads, this criteria has to be determined. So if C by D ratio, that is the spacing by the wave depth, is greater than equals to √2, then the required amount of the moment of inertia for the wave stiffener should be greater than that value, and the required amount of the required moment of inertia of the stiffener should be greater than that value. And if C by D less than √2, then the moment of inertia would be greater than that value. So these two values, from here the moment of inertia of the required moment of inertia is determined from that value. So from here the value of the moment of inertia will be calculated. From here we will assume one based on the required moment of inertia, the section for the intermediate transverse stiffener is chosen, and then the moment of inertia for the transverse stiffener is calculated, and which is greater than the MI required. It should be greater than the MI required. A section is chosen. Similarly, as in the case of normal bearing stiffener, then the section is determined. So the moment of inertia then again determined, and then it should be greater than the IS. That is the criteria we have to fulfill from that criteria, clause number 8.7.2. Now coming to the check for the outstand, it is similar here also. Outstand check, it is done from the similar formula, 20 TQ epsilon, 14 TQ epsilon, TQ is the thickness of the members. It is same in the case of bearing. Now coming to the check for the buckling, it is also same. Now the buckling for transverse stiffeners, should be checked for the buckling by checking its resistance to the force. Now the resistance to the force for the buckling stiffener, it is given here as per clause 8.7.2.5. This is the clause. The stiffeners not subjected to external loads, because the transverse stiffeners are only designed to resist the shear capacity, and should be checked for that value. FQ is equal to V minus VCR by gamma M0. It should be less than the FQD. So what is V, what is VCR, we will now see. What is VCR? What is VCR we know as calculated in the step 6. Let us go to the step 6. In the step 6, we have determined the value of VCR, that is the Vn equals to VCR. In the tension field method, we have determined the Vn equals to VCR. From there, we have to determine that value VCR. Okay, web panel design without using tension field method. So here that value has to be taken care. Now, so VCR we know. Now coming to V. Factor shear force, it is said there, adjacent to the stiffener. Factor shear force adjacent to the stiffener. That means if we are determining the shear force for the S1, we have to determine the V adjacent to that stiffener. So if we are determining the shear force for S1, we have to determine the shear force adjacent to the stiffener, that is S2. How it is determined? V is equal to Vz into L minus C by L. What is Vz? Vz is the shear force applied, actual shear force. L is the total length of the member, and C is the spacing of the two stiffeners. From there, the value of the V is determined. Now, that value we have determined. This is the value we have to check for that. FQ. This is the value which to which the intermediate transverse stiffener will be subjected to. So that value has to be checked. Now, then similarly the effective area for the total area under the buckling is determined from the similar formula here. This is the effective area under, to will act as a column. This is the effective area we have to determine from that. This is the same. Now, similarly as in the case of previous, now the IXX of the stiffener about the face of the wave is determined. Sometimes the wave stiffeners, this is the transverse stiffeners, are provided in two parts. It may be like that. It is the wave. This is one arrangement, and this is the second arrangement. This is the number one arrangement. This is the number second arrangement. If transverse stiffeners are provided on both sides, then IXX is determined at the center line of the wave. Center line of the wave. That's why we have determined for bearing stiffener at the center line of the wave. And if the stiffeners are on one side of the wave, like that, then the IXX is determined at the face of the wave. Okay, so we have to be clear of that. So if the stiffener, transverse stiffener or any stiffener is at the center, each stiffener at the two side of the wave, then we have to determine the IXX. There is the moment of inertia of the stiffener based on the center line of the wave, and if the stiffeners are only one side of the wave, like in the case of number 1, then the IXX is determined at the face of the wave. This will be the axis through which the moment of inertia will be determined. Then similarly R is determined, then the KL by rate should determined. So buckling class C, because solid section. Now the PD is determined, A effective we have calculated, and FCD we have determined from class C and table number 9C. It will be V determined, that is the V means that value. Okay, one second. It should be more than the value of the FQ, that is the shear force coming to the stiffener. We have determined that the value of the FQ here, so it should be more than the value of FQ. Okay, if it is not, then the transverse stiffeners we have to check again. We have to take another section for the transverse stiffeners. So this completes the design of the stiffener. end bearing and transverse. If then comes the step number 9. Now the design of the connection. Two connection will be there, as the transverse stiffeners are not load bearing connection, stiffener connection, as well as the connection for the wave to tip. So first the connection of the flange to wave, that means the flange plate and the wave plate, the connection for the main girder. First, for each flange to wale lengths will be there. For each flange, two wale lengths. So this is one flange, two wale lengths are there and two wale lengths are there. So for each plate, two wale lengths are there. So for QW, that is the value of the wale shear force, that is the V into F into Y bar by IZZ. IZZ is the moment of inertia of the whole section of the ZZ axis with parallaxis theorem. So we have to determine the moment of inertia for the whole axis here. Y dash is the distance of the CG of the flange from the CG of the total section. So this is the value of the Y bar, distance of the CG of the section from the CG of the whole section. V is equal to Vz we have calculated, and F is equal to area of the flange. We know what is the area of the flange? BF into TF. We know that. We have determined that. Now so we have got the value of the what is the force that will be coming to the weld. So we have to design the weld for that force. Okay, we have to determine the capacity of the weld, the strength of the weld, so that it can resist that force. Now, how to do that? Determine the effective throat first. A size of the weld is determined. Determine the effective throat thickness. Tt is equal to 0.7 into S. Then assume a shop or side weld based on that. Then determine the strength of the weld per unit length. So LW. If we can remember the formula for the weld, there is the formula Fy Tt Lw into 1 root 3 by gamma mw. So Lw will be 1 because we are determining for unit length. So Fw into Fi by Tt into 1 divided by root 3 into gamma mw, it should be greater than the Qw, that is the shear force acting on the weld. Okay, this is the design for the first design for the weld connection. Second connection will be connection to the end bearing stiffener with the wave plate. So there will be end bearing stiffener, the connection of the weld plate has to be determined for that. Okay, how to determine the connection for the end bearing stiffener for the weld plate? Now the end bearing stiffener will be connected with the wave plate, therefore the connection will be designed. Now for the accommodating fillet weld, the end bearing stiffener will be coped. As we are giving weld connection, this part will be coped so that to accommodate the fillet weld like that. So if this is the wave, so here will be the weld, here will be the weld. So this extra thing we have to cope. So we have to assume available. So we have to assume some coping length for that. This is the coping length. Okay. So the available length. This will be the now new outstand. So the available length for bearing Bs dash, the extra outstand equals to Bs minus coping length. Tension capacity is determined. TDN is equal to the following formula 0.9N. So N is equal to the, for that area, N is equal to Bs dash into TSP. That is the thickness of the plate. This is the TSP. Okay, this is the TSP, thickness of the stiffener. So Fu by gamma m1. So from here, the determining the shear per unit length you have to determine. So Q1 is equal to TDN divided by 2 into D minus 2 into coping length. From there, Y2. Now coming to Y2, because two weld lengths at each stiffener, 1, 2, 3, 4. So this is the connection for the stiffener with the wave plate. So wave plate. So this is there will be two connection for each of the two connection for the each of the what is that stiffener. So for there, why this is there 2. Now we have to assume the size of the weld similar. So this is the force that will be coming to the weld. So for fillet weld, effective throat thickness Tt is equal to 0.7 into S. Strength of the weld will be that formula. So this is the design of the connection. For the intermediate stiffener also, this formula will also be applicable. So assume the same value for the intermediate stiffener connection. Last thing, step number 10 is the check for the torsional resistance provided by the bearing stiffener. Moment of area of the end bearing stiffener about the center line of the wave should be. Now it is as per the clause number. Okay, let me pause here. So the step 10, the torsional resistance will be checked as per clause number 8.7.9, torsional stiffener. So clause number 8.7.9, the torsional check will be there. So Is should be greater than the that value. Is the second moment of area of the stiffener section about the central line of the wave, okay, should be such that Is, that is the second moment of inertia, that means the Is equals the moment of inertia of the bearing stiffener about central line of the wave, bearing torsional resistance of the bearing stiffener only. because bearing stiffeners are the load bearing stiffeners. Transverse stiffeners, intermediate transverse stiffeners are not transverse stiffeners, they are the shear to accommodate for the extra shear, but the bearing stiffeners are the take the extra shear force acting. So IS is the moment of inertia of the bearing stiffener, so the torsional check is only applicable for the bearing stiffener. So D, capital D is equal to the overlap of the, now capital D is equal to the overall depth, and TEF is equal to thickness of the compression flange that we know, and alpha x are determined on two values, LLT by RY ratio. So we have to find out first RY, that is the radius of the gyration of the girder along YY axis. YY axis you have to determine that. So there will be no parallel axis theorem required, because the girder is going, the y axis is going, it is a similar axis. Okay, so RY is so IY is determined, IY is determined. So for a plate girder, the IY is given at, this is the formula. If you can remember from the plastic analysis, this is the formula for calculation of the moment at YY axis. So IY by A is determined. So RY is determined. So LLT, what is the meaning of LLT? LLT, effective length from the table number 15. Let us go to table number 15 here. Okay, let us go to table number 15 here. Where is table number 15? Let us find table number 15. This is table number 16. Okay, we have come to that. Let us find table number 15. Here, fully restrained frame, warping, not warping, because we are here determining the torsional resistance. So warping will be there. So warping resistance in both frames 1.00 L. So from 1.00 L we will do, so here LLT will be 1.00 L. So putting the value here, we are determining RY. So determining the alpha x from here. So the torsional resistance, putting all the values, the IS, that is the moment of inertia of the whole flange portion or the stiffener portion of that about the center line of the wave should be more than that. If it is not more than that, we have to design for the extra torsional stiffener also. The torsional stiffener in the math that I have provided, there is no need of torsional stiffener. So this is always try to make the value in between that, so there will be no requirement any torsional stiffener. Okay, so this is the design procedure for plate girder. Please go through all the steps very carefully, and please remember how all the steps are coming, how all the steps are doing, and how the design steps are going. Stiffener design, plate design, wave plate, flange plate design, moment capacity check, shear capacity check, and the torsional resistance design. All the checks are to be done properly. Then only the plate girder design will be completed. So we will see one math in the next class. So this is that for today's class. This is up to today's class. We have seen how the design steps are going to helping us to design a proper plate girder. So this is for today's lecture. I hope you are all okay in your home, stay safe, and please study for your exam, because the college will open and the exam will start. I am assuring you that fact, and please go through that material, because a plate girder is a very common math. This math, I am doing the math like this math. One math will definitely come in your exam. One plate girder math of 15 marks. If you do all the steps, you will get the full marks. Please follow the steps and do the math in your home. Practice the math. I will show you in the next class. Okay, for today this is all. Okay, thank you very much for your time, class. Thank you very much.